Bismillahirrahmanirrahim. During the last session, we were talking about the convolution sum, and I have tried to give you a different perspective of the convolution, how to do it practically with a graphical representation as well as by the mathematical equations. I believe that we have covered up to the distributive law for convolution sum. Okay, so from the book, you can go through this causal linear time invariant system. So go through that. I believe that you will find it very easy. Afterwards, there's a stability of LTI system. Please read yourself. The examples are given in the book. Then comes the system with finite duration and infinite duration impulse response. We'll talk about these terms more and more in future. Just to give you the idea, this finite duration impulse response, in short form, we wrote it like FIR system, and infinite duration impulse response is represented IIR system. In case of FIR, your HN, that means impulse response, is a finite one. So you have finite number of values which can be used to represent your impulse response. From the graphical representation, we can show that, okay, we have this kind of impulses, maybe like this. This is our HN. Of course, this is a finite duration value. On the other hand, in case of IIR system, we have the impulse response which contain the infinite impulses. In mathematical term, we can write it like this. We have the value from, let's say, AK is a K is from minus infinity to plus infinity, and X, let's say N minus K. That means you have a lot of values which start from minus infinity to the plus infinity. So of course that shows that infinite response of the impulses. So we can see that whenever we want to find any output, that is nothing but your input signal and convolved with your impulse. Now, if your impulse is a finite element, finite duration impulse response, FIR system, then it can be realizable from the mathematical point of view, because in computer, what you need to do in convolution, you need to multiply, you need to do the folding operation, shifting operation, multiplication, and addition, and there are a limited number. However, if there is a IIR system, in that case, this is an infinite values of HN, which gives that practically for the computers, for the real-time calculation, this is not possible to do all the mathematical tasks. So that's why the IIR system can be represented in a different way, which is known as the difference equation. We'll talk about this in the subsequent section. The discrete time system described by the difference equation. This is the title. An FIR system is readily implementable directly as implied by the convolution sum, as we have already mentioned. If this is the convolution sum, and if this is the finite duration value, of course you can readily implement the convolution sum. If the system is IIR, however, its practical implementation as implied by convolution is clearly impossible, since it requires an infinite number of memory locations, multiplications, and addition. Why infinite number of memory locations? Because you need to put these impulses, and how many impulses you have? You have minus infinity to plus infinity. Of course, this is a infinite numbers. And how many multiplications you need? Definitely infinite, and also the summation. So practically, it is not possible for the computer to do the real-time calculation whenever it is a IAR system. So by conventional convolution equation is not a proper idea for FIR system to represent your final output. Okay. Then what is the solution? The solution is the difference equation. The difference equation can be represented in general by these two equations, where you can see that we have input side, we have the inputs. How many inputs you have? Of course, you have m number of inputs, and we have n number of feedback. Why it is a feedback? Because as you can find that when n is equals to 0, in that case, we'll have this value as y minus k, a k, and it is from k is equals to 1 to n. So you have how many values are there? You have n number of delayed, that means the feedback. If I represent that y minus 1, what does it mean? That means you have the output at this moment and the output previously you have. If I put y minus 2, means that you have this output y0 and delayed by 2 samples. Previously, you have the output previously is called the y minus 2. So if I represent like this, yn at this moment means this is your output, and you already have 2 outputs previously, that is y minus 1 and y minus 2. So how many delays how many initial conditions? Those are not the initial conditions. How many initial conditions do you have? You have capital N number of initial conditions. Why we are using negative value there? Just to make it convenient. You can put positive as well, no problem. But we are putting it negative. There is no harm to put negative here, because you do not know what is the value of the coefficient. If you are putting positive there, the coefficient will change accordingly. Okay. After that, you can put this section to the left so that everything looks very decent. That's why we are putting negative over there. And conventionally, we always put A0 is equals to 1. That means the coefficient with yn, that is always is equals to 1. And this is the difference equation. Any system, any discrete system can be represented like this. Yes, the system can be looks like this. Yn could be is equals to your k equals to 1 to m bk x n minus k. That means you do not have any feedback. Yes, it is one kind of system where this whole term is equals to 0. On the other hand, it might happen that you don't have any input. You only have the feedback. You do not have any input, you have only the feedback. It might also happen. So any sort of system, any extreme situation can be represented by this difference equation. And all the difference equation actually represent a filter. So it's also mentioned in the literature. Within the general class of IAF system, this family of DT system is more conveniently described by the difference equation. As I already mentioned, the convolution sum is not capable to represent the output for the IAR system. Now, new term is the recursive and non-recursive system. If you have the feedback from the output to the input is known as the recursive system. And if you do not have the feedback from output to input, it's known as non-recursive system. Okay, I'll just give you some example here. The problem, it has been taken from the book. Compute the cumulative average of a signal xn in the interval 0 to small n. So whatever the interval, you can take any value of the interval. So the system can be represented like this. We have the inputs from 0 to small n. How many inputs we have? We have n plus 1 number of inputs. That's why, just to make an average, we are dividing our input with this term n plus 1. So according to the system definition, this is our system. Now this system can be represented both by recursive one and non-recursive. Okay, let me show the things. As implied by equation number 1, the computation of yn requires the storage of, how many storage we need? All the input samples xk for 0 to n value. Since n is increasing, our memory requirements grow linearly with time. And that is very expensive from the computation point of view. So that means if you have a huge number of inputs, in that case, you need to put those inputs in a memory location and then add all those together and then divide it by the whole number. And that makes your life very difficult from the computational point of view, from the memory location. Now it can be also written, that means the previous equation, that means the previous equation was like this. Let me write it. Yn is equals to 1 by n plus 1 into x n minus k. Okay, so very small place. Yn, we need to do the summation for n equals to 0 to n. And we have n plus 1. But they are written as the value of the k. So if I write it like the k, okay, you can write it also like k is equals to 0 to n. Okay, now from there we can write this equation easily. So you can follow the terms and you will find it very easy. And this term can be also written like this from the fundamental equation, which means that this term is the output. This is the input plus this is the input at the current location plus other inputs, and the other inputs can be represented like this. Follow the equation and you will find it convenient. And from that equation, from this equation, you can also write it like this. Okay. So if I just give you the idea from this equation, what we have done, we are taking this n plus 1 in the left side, and we have this value. It can be represented like k is equals to 0 to n minus 1. So then we have xk plus, where is xn? N can be taken out of it. And what about this term? This term is nothing but whenever we are putting y, n minus 1, n is replaced by n minus 1. then everyone is replaced by that one. So we know that this yn minus 1 is equals to, if you put that value, what is n minus 1? N is now replaced by n minus 1 plus 1, and then this k is equals to 0 to n minus 1. Of course, n is replaced by the n and xk. From this, you can write easily. So they will cancel each other. What is the value? So you can take this n over there. So we can write that n minus 1 is equals to k equals to 0 to n minus 1 and xk. That actually been written in that subsequent section. So I believe that you got this point clear. So now this part can be written like this. Okay, finally, we got this equation, which has three parts. One is the final output. We have input, and we have the initial condition. Why that is initial condition? Again, for y0, we can write like this: 0 divided by 1. That means, of course, this is 0. Eventually, this is 0 minus 1. Whenever you are getting some value minus 1, that is called the initial condition. Even y minus 2, that is another initial condition. Y minus 3, that is another initial condition. So this term known as the initial condition. And by the block diagram, we can represent this structure with the following structure. That is, you can represent these things yourself with a different structure as well. However, we are representing here with the following structure. This is our output. You'll find that how we can write it. We have yn minus 1. So from the yn, we are putting a delay. So of course, this point is yn minus 1. And then yn minus 1 is multiplied with the value of n, which is a variable. So that's why the variable multiplication. And then it will be added with xn. It will be added. So our yn minus 1 will be added with xn. It will be added with xn. So at this point, we are getting the value like this: n minus 1 plus xn. And after that, we are multiplying with 1 divided by n plus 1. So 1 divided by n plus 1, 1 divided by n plus 1. So at this moment, that means the output gives you the total value: n divided by n plus 1, yn minus 1, plus 1 divided by n plus 1 into xn. Finally, you got this output. Okay. So why these block diagrams are needed? To represent your filter or your system, it is always important to represent your system with the block diagram. Then you can understand your system more clearly for the filter. Now, what we can see here, we need a very, very convenient computation process. Now the cumulative average yn can be computed recursively by multiplying the previous output value yn minus 1 by 1 divided by n plus 1, multiplying the present input by 1 divided by n plus 1, and adding the two products, which actually represent this equation. That means now what we can do, if we have the present input and previous output, then we can find our present output. We do not need a lot more memory locations. Basically, these delayed functions are the memory locations. You need to delay. How you can make the delay? That means you need to store the value. The previously available output should be stored somewhere, and that is the memory location. So how many memory locations you need for this system? Actually, you need one memory location. How many multiplier you need? You need two multipliers. there are 2 multipliers. How many adders you need? You need 1 adders. And that is very precise and very simple from the implementation point of view. And that is an example how this recursive system help us to implement a very complex system from the memory location point of view to a simple structure which need a very less number of memory location. The examples are given in the book. Please go through that. The linear time invariant system characterized by the constant coefficient difference equation. Basically, we are talking about the difference equation again, where of course they are having the constant coefficient. We are not talking about the complex coefficient. So let us start with a simple system, first order system. Here, this equation number 1 represents a simple recursive system described by a first order difference equation. Why this is a first order? How many delay values you have is known as the order of the system. So you have a single delay, so that's why this is a first order system. And of course, this is a recursive system because you need the previous output to compute your present output. So that's why this is a recursive and the first order difference equation. This is the simplest form. It might be complex. Okay, so first of all, we can represent this equation with the block diagram. This is a very simple system. You can do it very quickly. So this is our system. After having this system, we want to learn more about this system in general. Let me write those things. Y0 is equals to this from the equation. We have that equation as yn is equals to a yn minus 1 plus xn. From the fundamental equation, we can write it very easily. And after that, we can also write y1, and it is like this. Y2 is like this. If you can go up to yn, you can find this kind of equation. In general, what we can write here, we have again 3 terms. One is the output, present output. One is the initial condition, that is this term. And we have the inputs. And you find that there are some relation between this function to this power, function to this power, function to this power. So then we can write in a precise way. The elaborate equations can be wrote in a precise version. This is our final output, or this is our expression. This is our expression for what? Yn is equals to a yn minus 1 plus xn. So we have already mentioned that any sort of system can be represented by a difference equation, and this is nothing but a difference equation, of course. This first part contains the term y minus 1, we have already mentioned, is a result of the initial condition y minus 1 of the system. The second part is the response of the system to the input signal xn. So there are 2 terms, initial condition, and the other part is from the inputs. Of course, this part do not have any impact from the initial condition. On the other hand, this part do not have any impact from the inputs. So they are completely independent to each other. They are completely independent to each other. However, the final output, of course, dependent on both initial conditions and the input values, the input response. If the system is initially relaxed, what does it mean by the initially relaxed system? It means that you don't have any initial condition. That means y minus 1 is equals to 0. Thus, the recursive system is relaxed if it starts with 0 initial condition. Its corresponding output is called the zero state response or forced response and denoted by YZS. In this case, YZS, this y minus 1 is supposed to be is equals to 0 because we don't have any initial condition. And our zero state response is only depends on the input values, not to the initial condition. Can you give me one example where we need where we have the impact of the initial conditions in practical life or in your study? Do you have any example in your mind where you need the initial conditions to express the final output? Yes, 69.
RC/RL circuits.
RC/RL circuit. Why? Could you please explain a little bit more?
We have learned that if there was a source previously connected to that circuit and that's removed suddenly, then after we need to compute the previous conditions to find the final output.
Okay. Yes. I definitely appreciate your answer in a sense that, of course, the storage device like inductor and the capacitors, those are the storage device. They can store the energy. At the very beginning, if you don't have any energy to your circuit, definitely that is known as the initial condition 0. Whenever you have ran your circuit and after that you are putting another operation after time and time, definitely the previous voltages stored across the capacitor and the inductors work like the initial condition for the present calculation. Another very practical example can be given from the electrical machine. You have learned about the residual magnetism. In case of electrical machine, some kind of generation system need the residual magnetism for self-generating flux and eventually to generate the voltage and current. This residual magnetism is the initial condition of that system. Even though you do not have any input, since you have the residual magnetism, it can produce the output by itself. Okay, so I believe that you can understand what is the zero state response where the initial condition is equals to 0. Now suppose that the system described by equation 1, that means where we have both initial condition and the inputs, is initially non-relaxed. That means you have the initial condition and the input is 0. You do not have any input to your system for all n, so for all the time. Then the output of the system with 0 input is called the zero input response. Of course, there is no input, so that's why zero input response, or that is known as natural response, very logical names, or that is also called as free response, and is denoted by YZI. So in this case, of course, we don't have any footprint from the input. We only have the initial condition to produce the output, and that is known as natural response, free response, or zero input response. Now, as I already mentioned that those two outputs are independent to each other. Now, if we add those together for a particular system, then we can get the total response of the system. In general form, for such an equation is this one. We have already mentioned it earlier, and that can be represented like this, where we have also mentioned that the number of delayed, this capital N, is known as the order of the system. The examples are given 2.4.2 and 2.4.3 from the Procreus book. Solution of linear constant coefficient equation. It's a very, very, very important, very important topic. Please go through the book, the article number, as well as all the examples. Not necessarily, I'm writing here some examples. So there are a lot of examples, like this is 2.4.4, 5, 6, 7, 8, then 10. So all the examples, please go through all the examples are given in your book. This is very important for you. What is the motivation to do this kind of experiment, like the solution of linear constant coefficient difference equation? Why we need the solution? Because in some way, if you have the system response, you have the equation. From that equation, it is always convenient for us as an engineer to represent it with a mathematical expression and try to understand what would be the output for different cases. It is not always, or most of the cases, it will not be convenient to try all sort of inputs for a system practically, and then you will say that whether the system is stable, unstable, and how does the system will work. So that is why you need some system solution by the mathematical equations, and there you can put the values of n, and by there you can analyze your system response. And that's why this solution is very important. Okay. This part I have taken out of the book. So here I have presenting the solution for the difference equation by using the complementary solution and the particular solution. Okay, there are two ways to find the total solution. One is zero input response plus zero state response. You can add those together, or you can do, you have complementary solution and you have particular solution. Okay, the process is almost the same, but there are some differences. So here we are, I am using this format where I'm using the complementary solution and then the particular solution. After finding those solutions, we are adding those together, and we have found the coefficient by putting the initial condition. Okay, let me start the process. So the difference equation, first of all, we'll talk about the theory part. Don't be panicked with the theory, because after whenever I will go through the example, that will make your life easy, inshallah. So we have already mentioned that any equation, any system can be represented by the difference equation. This is a simple, you can say that first order recursive system, and this is a non-recursive system. In general, we can write it like this. Of course, we have a lot of initial conditions and a lot of input values. Solution of difference equation. This is the process. First of all, we'll explain, and then we'll give you a particular example. Of course, the yn is a function of your inputs and as well as a function of your initial condition. And the solution can be represented by the summation of the complementary solutions and the particular solution, where the complementary solution can be found by putting the value xn is equals to 0, because the complementary solutions, in that case, you don't need the input value, that is for the homogeneous equation. Need the initial condition to find the constant. We need the initial condition to find the constant, where the constant, the example will show us. I'm talking about this constant. It's like the constants are these from the example. These are the constant. Because as you know that for the complementary solution, you have the inputs are 0. And you can find those constant, of course, by putting the initial condition. We'll see that whenever we'll go through the example. For the particular solution, we need the value of xn, of course, and the name shows that this gives us the particular value by using the particular input. Try to understand that for a particular system, this is an arbitrary system, let's say this. You do not know what is your input. Of course, your output depends on your system response and also your inputs. If the inputs are changes, of course, the output will changes accordingly. Okay. So now, whenever we target the complementary solution, so the inputs are 0. So we'll start with this equation. This is called the homogeneous equation. And we try with our solution is equals to lambda to the power n. It depends on what would be the value of the lambda. Based on that, we can have the stable, unstable, or critically stable situation. So that's why we try this, since it can express as all kind of system. Putting that value with this to this equation, we can find it. From there, just doing the mathematical calculations, we can express it by this way, which is the characteristic polynomial of the LTI system. How many roots we have? We have definitely n number of roots. What are the roots? Lambda 1, lambda 2, lambda 3, up to lambda n. That is the set of roots we have. We have found those roots. Now the complementary solution can be written as alpha 1, lambda 1 to the power n. As we have start with yn is equals to lambda to the power n. Now how many roots we have? We have capital N number of roots. So that's why we can write it like this. Alpha 1, lambda 1 to the power n, plus alpha 2, lambda 2 to the power n, up to alpha n, lambda n, there is a mistake, lambda n to the power small n. And here we need to note that this is for the distinct roots. There is no common root. There is no common root in this case. So that means all the roots starting from lambda 1 to lambda n, all are different from each other. And we need to consider this note as well. Do not put the initial value here. So whenever we are finding the complementary solutions, we are not supposed to put the initial conditions to this equation to find this constant coefficient. We need to find the particular solution and then add those together plus particular solution. And in this equation, we need to put the initial conditions to find out those coefficients. Okay, so it is a note at this moment. We'll show the example in the subsequent section. Okay, so that is the process to find the complementary solution. Very, very easy and straightforward. Now for the particular solution, is of the particular solution is of the same form as the xn. That means if xn is a constant, k is a constant, then the particular solution must be like a constant. Maybe the value will increase or decrease, but it will be like a constant because you do not have any impact of the feedback. So that will follow the same pattern. If xn is sinusoidal, the ypn, that means particular solution, is also sinusoidal. So how we can assume this? That is the clue. Let xn is equals to like this, the ypn is like this, where the magnitude could be changes, the phase could be changes, but the pattern, what kind of pattern? This is sinusoidal, that will remain the same. On the other hand, if this is exponentially decaying or increasing value, it will be like the same whenever where the magnitude, that the multiplying factor might be changed. Okay, the pattern should be the same. Okay, so that is the note to find the particular solution. Another very important thing is here, if the roots are repeated in case of complementary solution, if the roots are repeated, what we can do, if first L number of repeated roots are there, then how we can represent it? Then the complementary solution would be like this: alpha 1 lambda 1 to the power n, alpha 2 n, and then lambda 1 to the power n, alpha 3 n square lambda 1 to the power n. If I make it very simple, then what we can say, for L equals to 2, that means if I have two repeating root, in that case, what I can do, alpha 1 lambda 1 to the power n plus alpha 2 lambda 1 to the power n, but I need to multiply another n, extra n over there, since they are repeating root. And after that, if I have, let's say, alpha 2, that is not the repeating root, this is alpha, let's say this is alpha 3 lambda 2 to the power n, then alpha 4 lambda 3 to the power n, because those are the distinct root. So whenever they are common, for each and every common root, you need to multiply with another extra n. And after that, for the distinct roots, that will be similar to the previous one. This is an exception that actually came from the mathematical concept. Okay, now we can move to a particular example, which will make our life easy. Let's take a very simple first order system, recursive system. Yn plus 0.5 yn minus 1 is equals to 2un. You can find that this is a step function. Okay, find yn for n is greater than equals to 0, and given that y minus 1 is equals to 2. Okay, so step number 1, we need to focus on the complementary solution. In the complementary solution, the input should be is equals to 0. Then the equation looks like this. This is called the homogeneous equation. For this one, try yn is equals to lambda to the power n, put it to this equation, and eventually we'll find this value. Lambda is equals to minus 0.5. So we can write the complementary solution is equals to a constant multiplied with this lambda to the power n, like a format alpha 1 lambda 1 to the power n, where alpha is equals to, here I put as a k, and lambda 1 is equals to minus 0.5 whole to the power n. So that is our complementary solution. do not put the initial condition here to find this constant. Do not put initial condition here to find the constant. Let it like this, and afterward you can find it where to put the initial condition. Okay, now in the second step we need to focus to find the particular solution. Here the input is a constant which is 2. So ypn is equals to k. Since that is a constant, we are taking a constant as well. You can also take it like k1 un. That is more logical. Okay, so you can take it like this, k1 un, because the input is like a pattern of 2 into un. So you can also take ypn is equals to k1 un. So from the equation, this is our equation. In the equation, what we can write, k1, because we have put it like this. So if you want to put un, you can write it, no problem. So in that case, this equation can be written as k1 un plus 0.5 k1 un minus 1 is equals to 2 un. Okay, no problem. You should write like this. Okay, so I should say that this is a wrong statement. You should write like this. In that case, what should be the value of n? For n is equals to, maybe there is some problem with the Wacom. Okay. Let for n is equals to, I'll take n is equals to 0. If I put n is equals to 0, in that case, okay, this is equals to 1. All the values you are getting 1. But what about this? If I put n equals to 0, it will be u minus 1. That means u minus 1 is 0. That means it will cancel this term. That is why I will not choose n equals to 0. I will choose n is equals to 1. If I choose n equals to 1, what will happen? k1 u1. What is the value of u1? Definitely 1. 0.5 k1 u, n is equals to 1 minus 1. That means u0. u0 is again 1, and is equals to 2 u1. u1 is equals to again 1. What does it mean? You need to choose the value of n in such a way so that all the terms here, all the terms number 1, 2, and 3, all the terms should survive. No one should multiply with 0 value. You need to choose the value of n in that way. Okay, so by choosing that, we can write the equation like this, and from there we can find the value k1 is equals to 2 divided by 1.5, which is equals to 4/3. This is our value k1. We have found the value of k1. Now what is k1? This is the particular solution. Now you can write the overall solution is equals to your complementary solution plus the particular solution. Now putting the initial condition. Now you can put the initial condition. Y minus 1 to this equation, y minus 1 is equals to 2. It is given, and then k minus 0.5, putting n is equals to minus 1, and then 4 divided by 3. From there you can find k is equals to 1/3 minus 1/3. So now you can find the value of k here. You can put the value of k there, and finally you found the solution. This is your solution. What is the advantage of finding this kind of solution? What is the advantage? The advantage is that now you can put different value of n, and you can draw your output, and you can analyze the system responsibility, the stability of the system, whether the system is stable, unstable, how that will behave by pen and paper, by doing the mathematical equation. This is the precise formation of the output by doing the solution of the difference equation. Okay. Up to this, do you have any question? Okay. Now, if we change the example in a different manner, let's say yn is equals to this plus this. The previous example was like this: yn is equals to minus 0.5 yn minus 1 plus 2 un. Now what we have changed, we have just only changed the input value. Of course, if you change the input value, of course the output will also change. What about the initial condition? It remains the same, the pattern, and as well as the initial condition is given as the same. Okay. So from this example, what we can expect, of course, for the complementary solution, we'll get the same value because we have the same equation. That means we can write yn plus 0.5 yn minus 1 is equals to 0. Try yn is equals to lambda to the power n. Put it to this equation, and you will find that lambda is equals to nothing but 0.5. And then you can write the complementary solution is equals to k, any constant, minus 0.5 whole to the power n. Exactly the same we have done before. And as you can see that we have the root is equals to minus 0.5. Be careful. And we have also found that here we also have the same root in the input. In the input, we have the same root. If you have the same root, that means you have the repeating root. The root is, in the complementary solution, we found the root is minus 0.5. And in the particular solution, if we want to let that what is the particular solution should be a constant. Previously, it was like this, but now, no, that is not like that. It's like this, the same pattern of this, of course, the same pattern, multiplied with the constant, of course, and there is extra n, because we have the repeating root. For example, if I have minus 0.4 there, minus 0.4 whole to the power n, in that case, this ypn should be like this, k1 minus 0.4 whole to the power n. Simple. Because it should be the n, of course, you should put un. Will be the same pattern, but this root is not a repeating root. That's why there is no n, extra n. But since there is a repeating root, that's why we are putting an extra n. Okay. Now you'll follow the same pattern, putting this equation to this putting this value ypn to the main equation. We find it, and as I already mentioned that if you take n is equals to 0 or n is equals to 1, in that case you will miss some term. For example, if you put n equals to 0, then this term will go 0. If you put n equals to 1, this term goes 0. Okay, but if you take n is equals to 2, in that case all the terms will survive. That's why we need to take n is equals to 2 there, and by putting that value you will find the k is equals to 1. It would be nice to mention is that even though if you can take n is equals to 3, 4, 5, whatever the value, for all the numbers, you will get the same output. K1 is equals to 1. You can try it. So now yn is equals to this, and we can write it like this. And similarly, put the initial condition, and from there you can find k is equals to 0. And finally, the output looks like this. This is the output we have found. So in the second example, we have given the essence of a repeating root. It can be a combination of repeating and non-repeating root, or it can be a repeating root from the particular and the complementary solution. Okay. Okay, I believe this is enough for today's class. In the next day, we'll try to cover up the other portion of this chapter, as well as we'll try to start our continuous time Fourier transform, though that should be covered earlier and you have the knowledge on that. Still, I'll give one lecture on continuous time Fourier transform, and subsequently I'll give the Fourier transform, discrete Fourier transform in the future classes. Before the meet, we'll just try to start those topics so that we can continue it after the meet as well. Okay, thank you very much for your presence. Thank you.